Greetings everyone. Welcome to part 2 of integrating rational functions. Hopefully you just saw my lecture on using division with rational functions. There's one other major skill that you need to be able to integrate a lot of the different rational functions that are out there. That one is going to be partial fraction decomposition. So some of the things that we divided in the last lecture, as you saw, I was able to integrate with using logarithms and inverse trig functions. But if the denominator is still too complicated, then you need to try and find a way to break it up more, or you may have to go back to trig substitution with completing squares and things like that. So this is what partial fraction decomp is. If I have some fraction where it's a polynomial of x on top, and then I've got some factors, something that I can break up in the bottom, then what I can do is I can turn this into separate fractions that each have one of those denominators, one of those factors as a denominator. So really what we're doing here is all algebra. It's reverse adding fractions. It's unadding fractions, right? So it's not subtracting fractions, it's unadding them. In other words, breaking them up into the separate fractions that each have different denominators. And what that will do is all of the denominators will then be simpler, and it will probably be some sort of integral that you can more easily approach individually. Since they're being added together, you could do them separately, right? So let's go through some different scenarios here first before we start jumping right in. If you have just a bunch of linear factors, then all you're going to guess, and that's what you have to do, by the way. You see the way I have the equals here? That's the way you'll be setting it up. You're going to guess some A is a number, over one of the pieces, B over another one of the pieces, C over another one of the pieces. That's little c and big C, by the way. Those aren't the same thing. Okay, so on and so on. If they're linear, then the numerator is going to be just a number. Okay, and the reason for this is because when you enter this, you should be checking that the denominator degree of your big fraction is larger than your numerator degree. Okay, if this isn't true, then you can do some sort of division first, like what we did in the last lecture. Okay, so once the numerator is a smaller degree, this is where you can go further and you can break it up. Okay, so then the denominator has to be a larger degree. That's why if we're doing all linear pieces, the numerators are just going to be numbers. So then move on down. What if I've got combinations? Like I have some linear and some not linear. Well, remember, as long as the numerator degree is less than the denominator degree, then that's what you want to fill out. So if I'm going to do a linear factor, right, x to the 1, then it's just going to be a number. But if it's a quadratic factor, then it would be x to the 1 in the numerator, or just a number. So you'd have a little bit of both, right? Could be possibly a linear and a constant. So let's say, for example, what if one of your factors here was a 4th power, right? That means your numerator could be something with an x cubed, x squared, x, and a constant, okay? The numerator is always going to be one less, okay? But there's a couple of exceptions. For example, what if you have the same linear factor repeated 3 or 4 or 5, whatever? I have 3 here, but it could be any number. Okay, it could be squared, could be 5th power, whatever. If it's the same factor over and over again, then I don't make one fraction with a squared underneath or on top of it. That would be what we've probably already got. Okay, so don't do that. Instead, what you want to do is write out all of the iterations that are possible from this factor. In other words, since I have it to the 3rd, I write it to the 1st power, to the 2nd power, and to the 3rd power. And I follow the idea of whatever the beginning one is. Since it's linear, it's just a number. So then as this thing grows, I still keep with just a number, even though technically this is a squared and it should be bx plus c or something like that. Okay, I'm going to stick with whatever the original one was if it's a repeated factor. Same thing goes with anything higher power. A quadratic squared, this should be a fourth power, right? Which means I should be expecting things with cubics in the top. That's not the way it works. If you've got a repeated factor, I write it in the repeated format where, notice, since this is just a quadratic, a squared, then the numerator can only be up to a linear. And then every piece after that follows the same MO, follows the same pattern. Okay, even though this is technically a fourth power, I only pick the CX plus D, the linear, because that's to follow the pattern. And the reason why the repeaters work like that is because I could try to get a common denominator here with these two by multiplying it out. And what it would basically be doing is just combining these things into one thing, and it would be what you would expect. But this is easier to resolve when we're solving for all of these missing numbers, the A's, the B's, the C's, things like that. Okay, so just be on the lookout. If you've got just singular factors, right? Linears get numbers on top, quadratics get linear and a constant on top. If it was cubic, you'd go even higher. But typically you can factor things at least into linears or quadratics. So that's why we kind of focus on those the most. Let's get a couple of examples of some setups here. Okay, so look, this guy right here, 1 over 8x minus x squared. I want to write that in a format that looks like some sort of polynomial function on top, which 1 technically counts as that, over some factors. Well, that means I need to factor this out. Okay, so that's what I'll do. I'll have 1 over x times 8 minus x, right? Now, once it's in that format, I can then begin making my other fractions that I want to break it up into, okay? I don't know what these numbers on top are going to be yet. That's the partial fraction decomposition algorithm. That's the thing that we're going to be doing in a minute. Right now, I'm just talking about the setup. So here, I'm going to have something over x and something over 8 minus x. I don't know what they are yet, but since those are both linear, I'm just going to put numbers over each one. And this is the beginning guess that you have that we'll be building our fractions out of as we do partial fractions. Okay, let's try again. Let's do the setup on this one right here. Again, I want to factor out the denominator, leave the numerator as is, x squared plus x minus 4 over, I'm going to factor an x out here, and that's going to give me x times x squared plus 4. So now I notice that one of my pieces is linear and one of them is quadratic. So if I'm going to start my partial fractions, my guesses would be I'm going to have something over x plus something over x squared plus 4. Those are my factors. And I don't know, but I don't know what the tops are yet, right? That's the process. But since this is x to the 1, it's just going to be a number, a. And since this is a quadratic, I can have bx plus c possible. And then we would figure out what the a, b, and c are, or the a and b are. That's the actual process of doing partial fraction decomposition. Okay? Here, this is just getting you used to seeing how we're going to do the setup. Okay? Next, we'll actually decompose these guys. Getting that setup correct is really half of the battle with partial fractions. It's just one of those skills you're going to have to practice and get used to seeing all the different pieces. And the more you practice, the more it will build and grow on you. Once you get the setup, then what you need to do is use a couple of these little techniques that I'll throw at you here for trying to solve, trying to figure out what capital A and capital B, or what A and B and C, or whatever pieces you happen to have whatever they are, okay? Now, there's a couple of different ways that people go. I'm going to show you the way that's always been quickest for me. Some people like to set up systems of equations. I personally find those to be tedious in these situations, and I like to do what we call temporary substitutions, okay? So from here, once you have your setup, what you notice is that you've got an equation, okay? Now, technically, x is a variable, and I'm going to treat him as such. However, a and b are the variables, the letters here that I want to solve for. I can still plug values into x if I want, but that would be just temporary because I need to keep the x eventually so that I can actually use these in integrals and actually make them generic fractions with the x's in the denominator. So, first thing you do is you make these things not fractions. That makes it easier to solve. In other words, I'm going to multiply both sides by this common denominator. Okay? So I'm going to multiply this. That's why I'm just going to wipe it out. And that means I'm going to do times x times 8 minus x times x times 8 minus x. I'm just multiplying it in all three places, and it just reduces here. So what that leaves me with is 1 is equal to a times 8 minus x plus b times x. Because notice I can reduce the x's here, and I can reduce the 8 minus x's here. And so I'm left with this equation. Whoops, brushed my finger on it. This equation right here is much simpler than that one, right? And I just need to figure out what my capital A and capital B happen to be. All right, so now what I'm going to do is that temporary substitution that I was talking about. So right here, what happens when x equals 0? When x equals 0, right, b times 0 is 0. And I picked 0 on purpose, by the way. I didn't just randomly pick it. I knew that it was going to wipe out one of my terms. And then 8 minus 0 is 8. So what I'm left with is 1 equals 8a. Right? Because 8 minus 0 is just 8 times a is just 8a. Well, I can solve for a now. A is 1 over 8. And I've got a. Okay, go back to the original equation. This is still my equation. What happens when x is 8? I picked 8 on purpose because 8 minus 8 is 0, and therefore it wipes this out. And so I have 1 equals b times 8. 1 equals 8b. Therefore, 1/8 is equal to b. Okay, well, I found a and I found b. Guess what? I could plug those back in over here and finish this out. In other words, 1 over 8x minus x squared, okay, must be equal to a over x. So that's 1/8 over x. And then b is 1/8, so that's 1/8 over 8 minus x. But of course, you know, we can clean this up a little bit. Let's just call it what it is. That's 1 over 8x. And this is 1 over 8 times 8 minus x. Or if you wish, you can put the 1/8 out in front and make it 1/8 times 1 over x and 1/8 times 1 over 8 minus x. That works too. Either one of these two is acceptable, because remember, our goal here is to be able to do integrals, right? So there's going to be something where there's an integral of this, and that was too complicated. So we break it up, and then I'll be doing the integral of the 1 over x and the integral of 1 over 8 minus x, which both of those are pretty straightforward and easy antiderivatives to do. Okay? All right, let's do this one over here. Partial fractions again. It's in the setup, right? I've got the setup for these two pieces here. And I'm going to approach it the same way. I'm going to multiply by the denominator so that I can make this a not fraction equation. So I'm going to multiply this x times x squared plus 4. So times x squared plus 4. And this whole thing times x squared plus 4. And of course, notice the x's will reduce here, and the x squareds plus 4 will reduce there, leaving me with this equation. X squared plus x minus 4 is equal to a times x squared plus 4 plus bx plus c times x. All right. So we can do a couple of things here. There's some tricks that do good when you mix them together. But the first thing that I see is that it'll be real easy for one of the letters especially because I can just let x be 0 again, right? If I let x be 0, so we just say when x is 0, like so, when x is equal to 0, then this is 0, I get negative 4 on the left-hand side. This is 0, so I get 4 times a, plus this is 0, and it multiplies out the whole thing. So I'm just left with negative 4 equals 4a. So in other words, a is negative 1. That's really crucial. Okay, so then what happens when you want to come over here and you want to try and zero this out? Well, there is a way to do that, but you would have to use imaginary numbers. And some people like doing that, and it works out really well for them. Other people don't tend to want to mess with the imaginary and complex values. Okay, so I'll avoid that for now, just so that you can see we can get by with really plugging in whatever we want. Okay, you can really plug in whatever you want here. But there are a couple of things I want to say here. I'm going to mix this with that other method that I was talking about before with the systems. I won't be solving any systems, but you do need to see sort of the approach here. Okay? So before I start plugging in more values, I want to show you something. Do you notice that a times x squared here, right? I also have technically b times x squared here. So if I were to distribute everything out like this, do you see that ax squared and bx squared are the only x squareds on the right hand side? And then x squared is the only squared on the left hand side. Okay? So this little maneuver here will save you a couple of minutes in your reductions here. What this means is a plus b has to equal 1. Now think about this for a second. There's an equality here, right? So if there's x squareds on this side and x squareds on this side, and they have to be equal polynomials, then a plus b, being the only squares here, right? I could reduce that into a plus b, would have to be equal to 1. So what I'm going to do is I'm going to write that over on the side over here. I know that a plus b has to equal 1. And normally that would be like the setup of a system, right? Especially if I had a couple of different things going on with a and b. However, I already know what a is, right? So I don't need to solve that like a system. I can then take the negative 1 and plug it in and solve for b. We'll do that in a second. Let's go ahead and finish out the equations here before we start solving any more. Next thing I want you to notice is there are no x to the 1s except c times x. Do you notice that? C times x right here? And there's x is 1 times x over here, right? So therefore, c times x has to equal 1 times x. It's the only singular x on this side and the only singular x on this side. Okay? So this mixed with this tells me that c has to equal 1. Well, all right, we're almost done then. We know that a plus b has to equal 1, but I already know that a is -1. So -1 plus b equals 1, which tells me that b is 2. And then we just saw right here that c has to be 1. Okay, now is there another way we could have gone about doing that? Sure. Could I have plugged in more x values? Yes, absolutely. You could plug in any value of x you want. In other words, if I didn't know the b and the c values, what I could do is plug in x equals 1. Okay? And if I plug in x equals 1, you'll get a number on this side, right? You'll get -2. And you'll get 5a plus b plus c. Okay? But I already know what a is, so you would get something with b and c in there. And then you would have to keep plugging in another number possibly. Okay? So there's just a couple of little, well, I call them tricks. They're just tiny techniques is what they are. Comes down to just comparing both sides of the equation or sometimes plugging in values for x. And it just comes out to practicing. Okay? If you're dealing with linear factors, the plug stuff is going to work really quick. If you're working with the quadratic factors, you may have to do a little bit of left and right equation comparison like this. All right? Now, I've figured out what A, B, and C are, and if you go back up to my setup over here, A, B, and C were the only things I was missing. So let's finish up this breakup here. This is telling me that x squared plus x minus 4 over x cubed plus 4x is equal to a over x, so that's -1 over x, plus bx plus c, so that's 2x plus 1, over x squared plus 4. Okay? So now we've successfully broken up this fraction into smaller fractions. And notice, each one of these would be a much simpler integral than the whole big rational function at the beginning, right? This would just be a logarithm. This one I could actually break up into a logarithm and an arctangent. Okay? But that's what you would want to do here. So I want to finish out one of these problems just so that we can see the full extent. Over the last 2 scenes, we've been breaking this one down and breaking it into the separate pieces and getting those pieces set up and ready. This is the end result. This is the goal. So you would have started with an integral of some rational function. And then after the decomposition process, you would then have multiple integrals for each of the pieces that you got. Okay? So keep in mind, this looks, straightforward and simple, but we've gone through a bunch of other steps coming up to this. And I'll do some more examples where we do it all at once in a minute. Okay, so let's finish this one up. The 1/8 from each one, I'm just going to factor that out from the whole thing. The integral of 1 over x dx gives me ln absolute value of x. And here, this one technically is a substitution where I need a negative, okay? Because the derivative on the inside here is negative. So technically I should be doing a minus minus. This negative will get sucked up in the du of the substitution. And then this negative right here will give me a minus. And then the antiderivative will be ln plus c. To succinctly make this, more concise, one other thing you could do is bring these two together in one function like this. Since it's a subtraction, you get division, like so. And this is a good place to leave your answer, although technically you could have left it here also. If you've been watching my whole series, I hope that you recognize this integral. 2 lectures ago in trigonometric substitution, we performed this same integral, but using trig substitution. And the process was to complete the square. And then this was the result that we got by doing all of the trig substitutions and then bringing it back out. So why does that look so different? They're actually equivalent. Let me show you. Right here on this guy, first of all, notice that the 16 minus x minus 4 squared is just the completed square version of this. So technically, it should look like this. Next, instead of just having the radical underneath here, I can actually extend it to where it's like this. Although there's a lot of little nitpicky details in there as to why, oops, forgot my square, as to why this, should be legal or not, just depending on what you believe and what you want to, hold it to. But basically, the square root of x squared, right, is the absolute value of x. So basically, all I did was just extend it and rewrite it. A square root is a 1/2 power. So I can bring the square root out with my logarithm rules as a 1/2 coefficient, and the 1/2 times the 1/4 would then give me 1/8 ln. And then notice this fraction right here, if I factor out the denominator, right, this fraction right here would be this, which the x squared over x I can reduce. So I'd end up with absolute value of x over 8 minus x plus c, which of course you'll notice is the same answer that we have just received over here. So they are equivalent. Do you have to go through all of these steps to show that? No, not all the time, but I wanted to show you that no matter which method you use, partial fractions or trig substitution, or even if you did something by parts, if you found a way to do that, okay? There's all kinds of ways to get to this answer, and they are equivalent. And which one is more work just depends on which one you tend to enjoy better, right? The trig substitutions may seem like a lot of work here because of the completing the square, but this guy's no slouch either with having to separate out the factors and then solve for the a and b parts. So it really, the most painless one is going to be your own opinion, whichever one the work speaks to you more. And not every integral it can be done with both. This is a good example of one that can be done. Some integrals really should be always done one way and others, another way, just depending on their original structure. Okay. For the rest of this video, I want to just work some examples from beginning to end, going through all of the processes that we have for integrating advanced rational functions. So we're going to start with the integral, break them down as much as possible, and then do the individual pieces at the end, one example at a time here. Okay, so I've got this integral here, 5x squared minus 12x minus 12 over x cubed minus 4x. Okay, so obviously this one is too difficult to do all by itself. I choose to do partial fractions because I notice that the denominator already has a greater degree than the numerator, so I can go ahead and just start breaking it into other fractions. So that's what I'm going to do here. I've got 5x squared minus 12x minus 12 over x cubed minus 4x, and I want to start breaking that down. So instead of the x cubed minus 4x, I'm going to factor that out by pulling out an x first of all, and that'll leave me x squared minus 4, which is a difference of squares, x plus 2, x minus 2. All right, so then that means they're all linear, none of them are repeating. I've just got a over x, b over x plus 2, and c over x minus 2. Then I multiply everything by this denominator here. I'm going to multiply all the whole equation by x plus 2, x minus 2. So it's going to completely wipe here, leaving me with 5x squared minus 12x minus 12. When I multiply here, the x reduces, leaving me with these two terms. So a, x plus 2, x minus 2. Here, the x plus 2 reduces, leaving me with the x and the x minus 2. And then in the c, when I multiply, the x minus 2's reduce, leaving me with the x and a x plus 2. Okay? So now, as I said earlier, whenever you're messing with just the linear ones and none of them are repeating, it's easy just to knock them out with a few x values. Okay? So let's start with when x is 0. When x is 0, this piece is going to eliminate, this piece is going to eliminate, those two are gone. And both of these are zeroed out. So I'm left with negative 12 is equal to, this is 0, this is 0. So I have 2 times negative 2 is negative 4a. When I divide both sides by negative 4, I get 3 is equal to a. So I've got my a value. Next, I'll pick when x is equal to negative 2. That will eliminate anything with the x plus 2 in it, because that'll zero x plus 2 out. On the left-hand side, I'll have 5 times 4 plus 24, so that's 20. 24 is 44, minus 12 is 32. And then I'll have b times negative 2 times negative 4. So that's 8b. All right, divide both sides by 8. And I get that b is 4. Next, I'll do when x is positive 2, because that'll wipe out anything that has an x minus 2. So that's zeroed out, that's zeroed out. I'm going to have 2 times 4, because 2 plus 2, right? 4 times 2 is going to be 8c. So I know that side is 8c. Over here, when I plug in 2, I get 5 times 4 is 20. Minus 24 is negative 4. Minus 12 is negative 16. Dividing by 8 now gives me that negative 2 is equal to c. Okay, so then my decomposition is such that 5x squared minus 12x minus 12 over x cubed minus 4x is equal to a equals 3, so that's 3 over x, plus b is 4, so that's 4 over x plus 2, and c is negative 2, so minus 2 over x minus 2. Okay, so I've decomposed the fraction itself into those. Back to the integral. For this integral right here, I can then say that this is equal to the integral of 3 over x dx plus the integral of 4 over x plus 2 dx minus the integral of 2 over x minus 2 dx. But of course, all of the numbers, the 3, the 4, and the 2 are just multiplied constants. And each one of these is just a simple ln integral. Okay, they don't even have each of the derivatives of the denominators is 1. So I don't even have to do any real substituting there. The final answer is going to be 3 ln absolute value of x plus 4 ln absolute value of x plus 2 minus 2 ln absolute value of x minus 2 plus c. And of course, knowing your laws of logarithms, you can simplify this into ln absolute value of x cubed, right, because the 3 comes in here, times x plus 2 to the 4th, that's his power here, divided, because of the subtraction, x minus 2 squared, and then plus c. Either one of those is acceptable, of course, but this is your final result of your integral. Next example, integral 4x squared over x cubed plus x squared minus x minus 1. First thing you're going to want to do is factor out the denominator there so that you know what kind of thing we're dealing with. I'm not going to be able to split up or do anything, and the numerator has a lower degree, so really your only recourse here is going to be partial fraction decomposition. But first I need to factor that denominator. You can factor that one by grouping. So notice that I can pull an x squared. That would leave me with x plus 1. Both of these have a negative 1, leaving me with an x plus 1. So then I have x squared minus 1 times x plus 1, which of course that turns into x plus 1, x minus 1. This is a difference of squares. So what I really have is x minus 1 times x plus 1 squared. That's the factorization of that denominator. So that means I need to break down 4x squared over x minus 1 times x plus 1 squared. They're both linear factors, but one of them is a repeat. One of them has the squared on it there. So then I'm going to have to do a over x minus 1, and I'm done with the x minus 1, plus b over x plus 1. No squared yet, right? Because if it's repeated, remember I do all the powers. And then just c over x plus 1 squared. Remember, that's because if it is repeated, even though this is squared, I don't have to put a linear up here. I can just keep the same pattern rolling all the way down. So when you have that repeated factor, right, just keep with the pattern, the b and then the c here. Okay, so when I multiply this denominator to all the spots, okay, I'm multiplying x minus 1, x plus 1 squared. So it's going to eliminate on this side, leaving me with 4x squared. Here it's going to eliminate with the x minus 1, leaving me a times x plus 1 squared. Next, it's going to eliminate the one of the x plus 1s. So that means b has x minus 1 and x plus 1 when I multiply this, because it's going to have two of these x plus 1 factors, and only one of them is going to reduce. So I'm left with 1. And then when I multiply here, I'm going to have c and x minus 1, because the x plus 1 squareds will reduce. Okay, so then I've got this equation to worry about. And I can get a couple of my values pretty quickly just by letting x be certain things. So for example, if I let x be 1, right? If I let x be 1, then this term is going to go away, and so is this one. So I'm left with 1 plus 1, 2, squared is 4. So I'll have 4a. And 4 times 1 squared is just 4. So this is telling me that a is 1. That's handy. Next, if I let x be negative 1, right, then everything with the x plus 1 will zero out. This will zero out. This will zero out. I'll be left with 4 times negative 1 squared over here, which will still be 4. But over here, I'll have negative 1 minus 1, which is negative 2 times c. So negative 2c. This tells me that c is -2. Okay? Now in this last one, what I can do is just let x be any value, or I can do the exponent analysis also. That also works. Let's do the let x be some value part, and then we can do exponent analysis another time. We haven't tried x equals 0 yet, and that's a pretty easy one to plug in. Here I'll get 0, and then here I'll get a times 1, which is a. Here I'll get b times -1 times 1, so that's minus b. And here I'll get c times -1, which is minus c. So this is telling me that 0 is equal to a minus b minus c. I already know what a and c are, so I'm going to get b by itself over here. I'm going to add b so that it gets to this side. In other words, b is equal to a minus c. But I already know that a is 1 and c is -2. This tells me that b is 3. All right. So then for my decomposition, I've got my a, my b, and my c. I'm going to decompose it like this in my integral here. So this is now the integral of a is 1, so it's 1 over x minus 1. Let's see, plus b is 3, right? 3 over x plus 1. And then c is -2. So that's going to be minus 2 over x plus 1 quantity squared dx. And of course, I'll be doing each one separately. Okay? This is an obvious one, right? The integral of 1 over x minus 1, that's just ln, absolute value, x minus 1. Same thing, but I've got a 3 multiplied on this one. So it's plus 3 times the ln of absolute value of x plus 1. Next, I'm going to go ahead and write this one out as an integral again so that we can talk about it. Minus 2 integral, and then I have x plus 1 to the -2 dx. This one was a squared in a denominator. Okay, so it's not going to be a logarithm antiderivative. It's just going to be a power rule. If you want to do a u substitution, that's fine. U equals x plus 1, but the derivative of x is 1, so substitution isn't totally necessary. You can treat this like a single variable with no change, right? So the power rule here is to add 1 to the -2 and go up to -1. The antiderivative then would be this. Divide by -1. That would be my antiderivative. Okay, now of course don't forget your plus c. And then let's go ahead and shrink wrap all of this together. I can bring both of these ln's together to make it a little bit simpler to write. I have ln, absolute value of x minus 1 times x plus 1 cubed. And then I've got a plus, this is going to be a 2. And then x plus 1 to the -1 is just x plus 1 in a denominator, plus c. All right, there's my solution to my integral there. Now I want to show you an example that has more complicated denominators than the one we've been talking about, with a much more interesting decomposition. So notice the denominator here is factorable into x squared plus 3 squared. So this is the denominator that I'm going to be dealing with in the decomposition here. Okay, so then I've got x squared plus x plus 3 over x squared plus 3 squared. So I've got a quadratic factor here, which means when I write my fraction pieces over here, like x squared plus 3, I have to do a linear numerator, not just a constant. So ax plus b. Now remember, this is a repeated one. Okay? So I start with a single, right? X squared plus 3 to the 1 power. Then I add another one with the squared power. And since it's a repeat of the original one like this, then I don't need to go up. I keep the same pattern. So this will just be cx plus d. And now my goal is just to figure out what a, b, c, and d are. Okay, so just like before, I'm going to take this denominator, whatever's over here on the left, and I'm going to multiply it everywhere. It's going to completely wipe out here, leaving me with the x squared plus x plus 3 equal to, I have ax plus b times a leftover x squared plus 3, because I'm multiplying by 2 of them, and one of them will reduce here. But in this next one, both of them reduce. I'm just left with cx plus d on that one. All right, so now on this one, I'm going to take a look at what I can plug in. And x squared plus 3 doesn't really have very many nice things to plug in to try and wipe something out. I can't just zero it out that easily. And cx plus d over here doesn't have anything multiplied by it to try and wipe that out either. So plugging in things to do direct elimination is not going to be as clear there. So instead, one thing you could do is the exponent analysis, where you analyze the left and right sides and then mix it in with a little bit of controlled substituting. Okay, so let me go ahead and write out the multiplication here so that we can compare and get a few of these pieces here. Okay, so if I multiply out this side, I've got ax cubed, because that's ax times x squared, plus bx squared, that's the b times the x squared, plus 3ax, that's this one, and then plus 3b, right? That's that last one. And then, of course, I still have plus cx plus d. Okay, so a couple of easy things that have already sprouted up. Notice there are no x to the third powers over here. There's 0 x thirds over here. What does that mean for a? Immediately, right? Right here, immediately, a has to be 0. Because there's no x cubes over here, and this is the only x cubed over here. Next, bx squared is the only x squared here, and there's a 1x squared over here. Okay, so that directly tells me immediately that b is 1, because it's compared to the only x squared on the left-hand side. Okay, and for these to be equal, both of these have to be true, because there's no other cubes or squares to be equal to the cubes and squares over here. Okay, so then let's finish up. Do you notice I have x and x here? So 3a plus c has to equal 1. That's both of these guys put together. Okay? And these last two put together here, 3b plus d, those are constants. There's no x's. So those have to be equal to 3. All right. Well, notice I've already got an a value for this one. So that's 3 times 0. In other words, c is 1. And I've already got a b value here for this one. 3 times 1 is 3, plus d is 3. So d must be 0. All right. So I've got a, b, c, and d, which means I'm ready to bring it back out to the decomposition and do the actual integral here. So this should be equal to the integral of ax plus b. Well, a is 0 and b is 1. Okay? So 1, 0 plus 1 is just 1 over x squared plus 3. And I'll go ahead and just put the dx and move on and split them up here. Plus cx plus d. Well, c is 1 and d is 0, so that's just x. Plus integral x over x squared plus 3 squared dx. Both of those are much more straightforward integrals than the original mess over here. Okay? This one is already ready to rock and roll. That's an arctangent integral. Okay? So I'm going to separate this here. This is equal to 1 over square root of 3 arctangent of x over square root of 3. You're just supposed to know that one, right? That's one of those antiderivatives you're supposed to know. And if you don't, you could actually use trigonometric substitution to get there as well. It wouldn't take too many steps. Next, I need to do a u substitution on this guy. Notice the grouping in the bottom. If I let u equal x squared plus 3, then du is 2x dx. Okay, so I have x dx, I need 2x dx. So if I multiply a 2 here, that would bring a 1/2 out here. And that's going to leave me with plus 1/2 integral 1 over u squared du. But of course, instead of writing 1 over u squared, I would rather u to the negative 2, right? Power rule, that becomes 1/2 u to the negative 1 divided by negative 1 plus c. Okay, and then of course this guy has been here the whole time. I'm just going to let him take a ride. So let's write out the answer here. I've got, this is equal to 1 over square root of 3 arctangent x over square root of 3 minus, right, because of the division by negative 1, so minus 1 over 2 times u. U to the negative 1, put u in the denominator with the 2. But remember, u is equal to x squared plus 3. So what I'm going to do is just say times x squared plus 3 plus c here in the end. Okie dokie. For the next few, or for the last few examples here, we're going to step it up a notch and mix in some of the stuff from the last lecture on division in with this stuff, because all of it is rational integration and it could all happen at the same time, which I'll show you with this example here. Notice the numerator is a higher degree than the denominator. That's the big red flag for, hey, wait a minute, you got to divide this out first and get the whole portion separate from the remainder portion. The remainder portion is a different story. That one may need to get broken up more. We'll see. Start with a division though. I need to actually perform this division. Okay? So I'm going to have in my denominator x cubed. Don't forget there's a 0x squared and a 0 constant. And in my numerator here, don't forget there's a missing x cubed power. So to do my division, I'm going to start with the top row, 2, 0, 9, 1, and negative 4. Right? That's 4, 3, 2, 1, none. I'm going to draw my line here, and I need 3 boxes. Okay? I don't need a division rule because there's a 1 here. but I'm going to count upwards. There's no squared, so that's a 0 for the squared. Minus 4 for the x, and there's a 0 for the number constant there. Okay? Since there is a cubed here, I have to shift by 3 diagonals. So 1, 2 diagonals, 3 diagonals. Right? And since this is an x cubed, then I can expect 3 remainder columns, right? Because I have to have number x and x squared that are less than x cubed. So technically my remainders are going to cut off here, right? These 3 columns are going to be remainders. All right, so let's fill in using our diagonals. My first column is already ready to go with a 2. Then I do 2 times 0 is 0. 2 times negative 4 is negative 8. 2 times 0 is 0. So I did my diagonal there. Next, I add up these zeros. I get 0. 0 times 0 is 0. 0 times negative 4 is 0. 0 times 0 is 0. And I've hit the top there, right? The top end. Remember, once you hit the top end, that's done. The rest is just shift. So I'm going to be shifting 2 diagonals here. Okay. So let's add up the rest of our columns here. I have a 1, I have a 1, and I have a negative 4 here. Okay. So what does this division tell me? It tells me that this becomes the integral of the whole number 2, right? That's the numbers, then that's the x's. It should make sense because 4 minus 3 is 1, so I should have 2x to the 1. 2x plus, now the remainder portion. I've got number x and x squared. That's going to be x squared plus x minus 4 over the original divisor here, x cubed plus 4x dx. Well, okay. So the integral 2x part, cinch, power rule, right? We've already got that part figured out. Okay? But I can't integrate this yet. It's not broken up enough. I now need to move on to a partial fraction decomposition. So I've got x squared plus x minus 4 over x times x squared plus 4, right? Because I factored it out, the denominator there. And that's going to be equal to a over x plus bx plus c over x squared plus 4, because I have one linear and one quadratic form, right? So the linear has a number, the quadratic has a linear n number on top of it. I multiply by this denominator, which is then going to give me this, and then a times x squared plus 4, and x times bx plus c, after reducing the multiplications of that denominator. This one is going to be pretty straightforward after a direct comparison here. Notice that I've got ax squared plus 4a plus bx squared plus cx. Okay? Now, of course, that's equal to all of this. Let's start with the number. You see 4a is the number portion here. It's equal to negative 4. Negative 4 equals 4a. Therefore, negative 1 is a. Next, go with the cx. That has to be equal to x. So immediately, c is equal to 1 because it's the only x on both sides there. Okay, now lastly, these two put together are both my squares. I have a plus b is equal to the only x squared over here, which is 1. But I already know what a is. So negative 1 plus b equals 1. Therefore, b is 2. Okay. So now this is the integral that I have. I have the integral 2x, which is still there, plus, I figured out a was negative 1. So I'll just put minus actually, minus 1 over x, plus bx plus c. So that's going to be 2x plus 1 over x squared plus 4 dx. I realize we probably did that one earlier, but I wanted to put all the work together so that you could see all of the work in one problem at the same time. Okay, we're almost ready to finish this one up. This one is not exactly right for a substitution. Okay, these two are perfect. This one has too much going on in the numerator. We're lucky though, numerators are easy to split up. So instead of writing this in this form, 2x plus 1 over x squared plus 4, I instead want to opt into splitting it like it is. So instead of 2x plus 1 altogether, I'll do 2x over the denominator, that's just the bx over it, and then plus I'll do the c then over it by itself. So that'll be plus 1 over x squared plus 4 dx. Now each one of these is perfect for a integration. Okay, so equals, antiderivative of 2x is x squared. Next I have minus ln absolute value of x. This is a substitution, but notice I don't have to fix anything. Here, if I let u equal x squared plus 4, then du is 2x dx, right? I've already got that, 2x dx. So in other words, it's perfectly 1 over u, which means I'm going to have plus ln absolute value x squared plus 4. And then this last one is an inverse tangent. So plus 1 over 2 arctan x over 2, and then plus c. And of course, well within your rights to combine this, the two logarithms as well, or you can leave it in its current form. Both are quite acceptable. Okay? Let's go out with a bang. Here's the doozy that we did back in the last section. Let's tie it all together and find an antiderivative for this monster, right? Okay, so I've got this fraction, and the first thing I notice is that the numerator has a higher degree than the denominator. So I need to divide first, right? Let's do that. I'm going to line up my numbers from the top. That's going to be 3, 17, 7, 17, 13, and 6. I'm going to draw a line. It's x to the third, so I need 3 boxes, but I also need a division by 3 rule. Okay, so I've got 3 boxes, and then I've got another division by 3 rule standing. Since this is a cube, 3 of these are going to be remainders, so I'll just fill that in here. Alrighty. Then my divisors, I have -2, -3, -2. Okay. Since it's a cube, I have 3 diagonals of shift. 1, 2, and 3. Okay. That also means I can expect the other 2 diagonals of shift over here. Alrighty. Let's go. So add up to get 3. That's 3. Divide by 3, I get 1. And that's the number we multiply, right? So 1 times -2 is -2. 1 times negative 3 is negative 3. 1 times negative 2 is negative 2. Add these up, I get 15. Divide by 3, that's 5. 5 times negative 2 is negative 10. 5 times negative 3 is negative 15. 5 times negative 2 is negative 10. I add these up and I get negative 6. Divide by 3, that's negative 2. Negative 2 times negative 2 is 4. And negative 2 times negative 3 is 6. And negative 2 times negative 2 is 4. Okay, so I hit the top end of the diagonals there, and all of my columns are ready anyway. So 17 minus 17, then plus 4 is 4. These don't have to follow the division rule though, because these are the remainders. 3 and 6 is 9. 6 and 4 is 10. All right. So let's draw the line here. And let's use this to rewrite this integral. So now I have the integral of, remember this is the whole part, this is the remainder part. So I've got number x squared. So that's x squared plus 5x minus 2 plus the remainder 4x squared plus 9x plus 10. 4x squared plus 9x plus 10. My dx is going to go there. And my denominator has not changed. 3x cubed plus 2x squared plus 3x plus 2. Okay. And of course, that's the thing I need to split up further, right? Because obviously these three are just little power rules. I need to do a partial fraction decomposition on that guy. First, I'll need to factor this. Notice that I can factor by grouping again. Like so. So I'll have 3x plus 2 times x squared plus 1. This is what my denominator factors out to be. So I'm doing a partial fraction decomposition on 4x squared plus 9x plus 10 over 3x plus 2 times x squared plus 1. I have a linear and a quadratic, so that's just going to be a over 3x plus 2 plus bx plus c over x squared plus 1. So when I multiply this denominator to both sides, I have the equation 4x squared plus 9x plus 10 is equal to a times x squared plus 1 plus bx plus c times 3x plus 2. Alrighty, so let's see. Anything that can quickly get me through here? Yeah, let's try x equals 0 first. Leave a little space for exponent comparison later. I'll leave another line open there. So that's going to give me 10. And then if this is 0, I get a. This is 0 and this is 0. So I get 2 times c. So plus 2c. Okay, so I can't do anything with that yet. Let's do some more comparisons. Okay, so if I multiply out everything here, I'm going to have that this is equal to ax squared plus a plus 3bx squared plus 2bx plus 3cx plus 2c. All right. So I'm noticing that that's not going to totally help because I already know a plus 2c equals 10. That's the numbers, right? We already got that. A plus 2c is going to equal 10 still. but now I also know that a plus 3b, the squares, has to equal 4. Okay? And then I also know that from the linears here, 2b plus 3c has to equal 9. And try as we might, unless you want to start throwing in complex and imaginary numbers, which you can do that to sort of try and eliminate some things. The really only other thing I could do is plug in a fraction, which wouldn't be as fun. So the path of least resistance here is really just go ahead and go on the old school way of solving the system. Notice I've got A and C, A and B and C together. All I really need to do is substitute one of them somewhere here and sort of just wrap it all up. Okay, so let's see. If I solve for A here, A is equal to 4 minus 3B. And I can plug that one into here. That's going to tell me that 10 is equal to 4 minus 3b plus 2c. Okay? So I subtract the 4 from both sides and I get 6 is equal to 2, well, let me go ahead and put them in order. Negative 3b plus 2c. Okay? So I will put these two equations together. That's going to be 9 is equal to 2b plus 3c. Gotta love that, right? And then I'm going to multiply these two equations to do an elimination. So let's multiply this top equation here by 2 and the bottom equation here by 3. Okay. So let's see, I'll have negative, well, let's see. Okay, so what does this become? I have 12 is equal to negative 6b plus 4c. And right here, 27 is equal to 6b plus 9c. So when I add those two together, my b's will eliminate, leaving me with 39 is equal to 13c. So in other words, c is 3. Okay, so if I know that c is 3, I can come over here and find out what a is, right? If c is 3, then a plus 6 is 10. So a would have to be 4. And if a is 4, right here, 4 equals 4. If I subtract 4 from both sides, I'll have 0 is equal to negative 3b, so 0 is b. All right, so we got A, B, and C now. Let's separate this out. Okay. My integral has become x squared plus 5x minus 2 plus, I have 4 over 3x plus 2 plus, b is 0 and c is 3. So that's just 3 over x squared plus 1 dx. Power rule, power rule, power rule, logarithm, inverse tangent. Right? So final answer here, 1/3 x cubed plus 5 halves x squared minus 2x plus, now be careful, the 4 is along for the ride, the inside derivative is 3, and I would have to accommodate that with a substitution, so you'd end up dividing by 3. ln absolute value 3x plus 2. I don't have enough room left on the line there, so I'll have plus 3 arctangent of x over 1. I guess I could just put x, sorry, plus c. Okie dokie. So I hope that this has helped you see all of the methods that we have for breaking down, simplifying, and then integrating the pieces of rational functions.